Hello students, in this video I'm going to answer this question. Calculate the electric field E at the point P due to a charged thin spherical cell. Spherical cell means inside the cell, it is empty inside the cell. Okay, that means it is hollow. Okay, if the point P is, there are three cases: outside the cell, on the surface of the cell, and inside the cell. So here you can see in the first case, if the P is outside the cell, then what will be the electric field at this point? And if P is on the surface of the cell, when small r is equal to capital R, where capital R is the radius of this cell and small r is the distance from the center to the point P. Okay, so in the first case, small r is greater than capital R. Second case, both are equal, small r and capital R, right? And in the third case, small r is less than capital R. That means this P lies inside the cell. Okay, so this question was asked in 2020 Assam Higher Secondary Education Council AHS second year exam, AHS final exam. Okay, so before we start, please subscribe the channel, hit the thumbs up button, also share with your friends. It's for me to create new contents for you and help me to grow my channel, right? And if you want to follow me on Insta, this is my Insta ID, OZHALAKHYAJIT, OZHALAKHYAJIT 123. This is the Insta ID. So now let's start. Electric field at P when it is outside the cell. So let me draw the cell here. This is the cell, suppose, and it is charged, uniformly charged. Let me consider here, this is positively charged cell, and charges are uniformly distributed over the surface of this cell. And here is the center. Suppose this is the center of the cell and its radius is capital R. And there is a point P. So let me take the point P here. This is the point P, right? This is the point P, and distance between the center and the point P, this is, suppose, small r. Let it be small r. Okay, let it be small r. Okay, so here small r is greater than capital R. Okay, so here distance, here you see small r is the distance from the center of the cell to the point P, and capital R is the radius of the cell. Let me take that way, right? So let me just adjust this figure here. Okay, so in order to find the electric field at this point P, so let me draw a Gaussian surface here through this point P. Okay, suppose this is a Gaussian surface through the point P. Just wait. So let me draw a Gaussian surface just through P, through the point P. Okay, whose radius is equal to the distance between P and the center O, right? So let me take that way, right? So this is the Gaussian surface. Now you see, just wait. Now let us consider a very small area element at the point P. So that is, suppose, ds. This is ds, and as I have considered this sphere is positively charged, so direction of the electric field, that should be radially outward in this direction, right? That should be the direction of electric field, and the area vector to this small area ds, that should be directed in this way, in the direction of electric field. So let me take the unit vector along this area vector. Let me write the P here. Just wait. This is the point P. Okay, just wait. Let me write here. This is the point P. Just wait. Okay, so let me write ds here. So this is ds, and the this is the n cap along ds, and the area vector is ds vector. Okay, n cap is the area vector along the n cap is the unit vector along the area vector. Okay, let me consider that way. So now you see, according to Gauss theorem, you see, now flux through this Gaussian surface we have drawn. So let me mention about the Gaussian surface here. Just wait. Let us draw a Gaussian surface. Let us draw a Gaussian surface of radius r through the point P, right? Then flux through this Gaussian surface according to the Gauss theorem, we get according to Gauss theorem, flux through the Gaussian surface that should be given by phi is equal to integration surface integral E dot ds, right? E dot ds, that should be is equal to charge enclosed by the Gaussian surface divided by epsilon naught. This is the Gaussian surface, right? So here q is the charges distributed over the surface of the cell, right? So this total amount of charge distributed over the cell is suppose q. Let me take that way, right? Now you see what we can do here. So here also let me mention one more thing, that just wait, let me write this things here. Okay, so ds is very small area element at P, and n cap is the unit vector along the area vector ds is the small area element at P, and n cap is the unit vector along the area vector ds, right? So we have it in that way, right? So this is the n cap, which is nothing but a unit vector along ds vector, that is area vector, right? And ds is the very small area element at P. Okay, so now let me go to the next page, next slide. Okay, so let me copy this last step and let me take a new slide. This is the new slide and here is the last step, and let me copy the diagram as well. Just wait, this is the diagram. So here is the diagram. Okay, right? So now you see here, you know, this E dot ds, that gonna be E ds cos theta, and here theta is the angle between n cap and this electric field. So that's why which is equal to 0, which is equal to 0 here. Both are directed in the same direction, so here we're going to write cos 0 here, q by epsilon naught, and e integration of ds. Cos 0 is 1, q by epsilon naught, so ds gonna be equal to if you integrate ds, if you integrate this area, you're gonna get the whole area of this Gaussian surface whose radius is small r. So area of this sphere, we know that 4 pi r square, that is the area of a sphere, right? So here we can write surface integration of ds, that is equal to 4 pi r square, right? So that's what we're going to have. Now from here we're going to get the expression for electric field is this 4 pi r square epsilon naught, right? So now this is in scalar form. So in vector form, what are you going to get in vector form? So we know the direction of this electric field. Here you can see that is in this direction along n cap. So we can write the vector form this way: q by 4 pi r square epsilon naught n cap. That's going to be the vector form of the electric field. So here you see this is the expression, this is the electric field at P due to the cell, right? And it is same as, so let me write here, and it is same as the electric field due to a point charge q at a point P, which is r distance apart from Q, right? So now you see this expression also can be expressed in terms of surface charge density. And before that, let me tell you something. So here you see this expression, if you see the expression, this is same as the expression of electric field at a point P, which is at a distance r from a point charge Q. Okay, so that is also electric field at this point E is also Q by 4 pi r square epsilon naught n cap. If you draw a Gaussian surface through this point, then you're gonna get the same expression, right? So hope you have understood this. Now you can express this result in terms of surface charge density as well. So let me copy this figure let me copy this figure and let me go to a new slide. Okay, let me go to a new slide. So we have done got this required expression for the first case. Okay, for the first case. Okay, this is the expression of electric field at point P due to the cell when P is outside the cell. That means small r is greater than capital R, right? And it is same as the electric field due to the point charge Q at a point P, which is r distance apart from small q, right? So now in terms of let me take this is equation number suppose 1. Let me take this is equation number 1 and this is equation number 1, right? So now in terms of surface charge density, in terms of surface charge density, Now you see, if you see the diagram, just wait. Let me copy the diagram. Take the screenshot. Okay. So here you see, this is the diagram. So here we have Q amount of charge distributed over the surface of the cell, right? So then surface charge density sigma, that's gonna be equal to charge distributed over the surface divided by surface area of this cell. So that means charge per unit area. Okay, and the surface area of this cell whose radius is capital R, that's gonna be 4 pi capital R square, right? So now from equation number 1, here you say this is the equation. Let me copy this equation number 1. This was the equation number 1. Here you can see, right? Okay, so now you see, let me write here. Just wait. So this is from 1. Let me write from 1. From equation number 1, we have got this equation number 1. Now we can replace Q by sigma 4 pi capital R square. Okay, let me use this here. This is suppose equation number 2. Okay, so if we use this one here instead of Q, that is sigma 4 pi capital R square pi R square epsilon naught, just wait, divided by 4 pi small r square epsilon naught n cap. So using 2, then what we're gonna have? So here you see 4 pi cancel, then this expression becomes this: electric field E sigma r square by small r squares epsilon naught. So you're gonna get this, right? Okay, now let us take this equation as equation number 3. Now let me copy this equation number 3 and let me go to a new slide. So here is the new slide. What was the last expression? This was the last expression. So when r small r is greater than capital R. Now let us take the case of number 2, that is when small r is equal to capital R. That means when electric field at P, this is on the surface of the cell. Okay, so let me redraw the diagram for this case. Right. So here is the diagram. This is the diagram for this case. So here the point P is on the surface where small r is equal to capital R. This is the positively charged, uniformly charged cell. Okay, so in this case, if we use this condition in this above equation number 3, okay, putting small r is equal to capital R in 3, what we're gonna have? We're gonna have electric field E, that's gonna be equal to sigma, instead of capital R we're gonna put small r square by small r square into epsilon naught n cap. Then here this r square cancels. In that case, what we're gonna get? We're gonna get the electric field E, that's gonna be equal to sigma by epsilon naught n cap. That is what we're gonna have, right? Now you see, if you use this relation in equation number 1, what was the equation number 1? And we have got this one from equation number 3, right? From equation number 3 in terms of surface charge density. If you write in terms of charge Q, then this is the equation number 1. So if you put small r is equal to capital R, then this expression becomes this: E is equal to in terms of Q by 4 pi capital R square epsilon naught n cap. That's what we can have, right? So hope you have understood this. Or you can write this way, just wait, epsilon naught here, r square. So you can use this expression as well, and this is in terms of surface charge density. Now what will be the electric field for the third case, number 3? If P is inside the circle, inside the cell, if P is inside the cell, that is capital R is less than small r is capital small r is less than capital R. Let me redraw the diagram. Just wait. This is the third figure. So here you see, in this case, if you draw the Gaussian surface here, then this Gaussian surface doesn't include any charge, because the charges are distributed over the surface only, surface of the cell only. So that's why if you draw a Gaussian surface through this point P, which is inside the circle, so charge inside the Gaussian surface, that's gonna be 0. So now you see, in this case charged enclosed by the Gaussian surface is 0. That means Q is equal to 0 here in this case, right? So therefore electric field at P, so therefore we can write electric field at P is equal to 0, because if you put 0 here, then this expression becomes 0. Okay, when for the third case, if the P is inside the cell. So hope you have understood this, and thank you for watching. See you in the next video. Okay, bye bye.